Okay, so now you see we have our speaker, and let me briefly introduce him. I mean, if we want to go through all the details, it's going to take me hours. So Professor Kokossis received his PhD from Princeton University, and after a long-term career in the UK, I think you got Surrey, right? He returned to Manchester as well. He returned to Greece, where he was holding a position as a professor and also center director, leading many large EU projects. He's also holding a visiting professorship in Imperial College London, maintaining his connection in UK, also in the US. So he's one of the leading research in the broader area of energy systems engineering, sustainability, circular economy, and I think that's the topic of today's presentation. He has a long list of honors and awards, which I will not list because we are a bit tight on time. But please join me to give him a very warm welcome.
Here's the advance.
Back and forward, yeah? Okay. So thank you very much for this generous introduction. It's a special pleasure, to be here and deliver this kind of seminar for a number of reasons. One of the obvious one is that Cornell has this excellent reputation of producing impactful, quality, fundamental research of the type of the research I have been, enjoying, since my years at Princeton University. I remember late Chris Fludas has had a lot of exchanges with the place and operations research group here. And apparently, the other reason is that systems engineering, thanks to FNG, has been everywhere in chemical engineering, in all kind of corners. So you anticipate you're gonna benefit from interactions with his beautiful group. From my side, this presentation is apparently in systems engineering, with a big claim that systems engineering, more often than not, has much more importance, than the individual technologies that you try to integrate. This is a claim that I will try to justify, in the following slides. I understand we have lost some time, good time, as you waited for me to come from the hotel, but I can go through the main parts of that, and of course, we can discuss after that, what are your overall views, on this matter. I said I have special reasons to be also pleased today, because other than your Ithaca, this other Ithaca in Europe, is the place where I come from. So
original Ithaca.
Yeah, well, my roots are from this Ithaca. It's not Greece, it's Ithaca per se. Yeah. And I don't know how much, and for those of you who may not be familiar with the Greek mythology, Ithaca stands as a symbol for unswerving commitment to life. And as a title, it is a very celebrated poem, Ithaca. Ithaca stands, accounts for the actual essence of life. So you can tell, I can be, very touched by all that. So no more poetry, no more literature, but I would like to just give a mere reference to my employer, which is the National Technical University of Athens. This is the first choice for engineers, first choice for students, overall. And it's not the largest, but as I said, it's the first preference for students at the university. It's a natural exporter of people around the world, so many of our graduates, you have seen at the departments in the US, but not only, nowadays many more in Europe. So, as I said, I will start with some introduction, quick introduction, as we lost time, where I'm trying to explain what we exactly mean by integrated approaches or systems approaches, starting probably with the business and the environmental drives that have taken us to renewables. There is little to say about renewables. Obviously, that they're very important, things to consider for climate change type of challenges. It is about sustainability and the future of our planet. It is also about energy security, but it's also about economical kind of drives, and jobs and new technologies, new innovations. So this is all about that. It is interesting to know that it's not the chemical engineering community that is interested in that, it is all the other community. It is the Facebook, the Microsoft, it is Google that is investing much, much more in renewables than what the chemical industry does. But of course, chemical industry is doing a lot of that. Also, regarding climate change legislation is driving towards this direction. And after all, chemical engineering has the legacy on dealing with chemicals overall. So it's a natural kind of knowledge and expertise that can be exploited. And this kind of stuff can be even more intensive because to consider aspects and challenges of circular economy. Remember that in circular economy, most of the streams that are involved are organic streams. So you can tell that the new chemistries that need to be developed will come from domains like us. And I like this slide, to remind people that out of all renewables, many people think about solar, about wind, about this being more important. But if you really see the fraction of biomass in these renewables is by far the largest part of renewables. So from all the renewables, biomass is the most abundant, is the most promising, and is the only one which is related to carbon. Carbon has been the basis of most chemicals that we see today. This is a picture in Europe in terms of emerging biorefineries. You have, you can see here lots of different developments, promising new jobs, it's lots of investment that goes behind that. So what is the main drive behind that, or what is the main need behind that? The main need of all these kind of new developments is to scale up efficiently so that you can compete with fossil-based type of options of that sort. And this is where, again, the most of the help is there. And where chemical engineering again stands for that? Well, we have this legacy, this historical kind of experience. Remember, we have been the ones who started the conventional refinery. And for those of you who like history and want to go back and see what happened back then in those times, they were subsidizing the use of oil, of fossil oil, against biodiesel, So that was the time then. So, and also they started making easy use of oil and discarding the rest of that. Now, getting into the point where every drop of oil comes into something useful, It's a very integrated, very efficient type of industry. Against this background, we have to come up as engineers with process systems engineering has an important role because it has capabilities and tools to synthesize, to come up with options, screen different options. It has technologies to build efficiency through process integration, and of course through modeling, simulation, and all this kind of model-assisted tools. It can scope, and analyze and scale up different things. So again, how the situation looks like today. We want to go there or where we are now. So I quote my good friend Michael O'Donoghue from the IBISBA research infrastructure in Europe, who makes this parallelism of the state of the art, today, or state of practice, with this beautiful termite, So this termite has nice guts, It has developed a nice meat part, And what it comes to develop is its tailgate, the final part. So this is how the whole situation can be parallelized. And in systems parlance, you can give this definition of the problem as follows. Given I have some chemistries which have some promising footprints, so what I want to do is I want to scale up so that I have a holistic full use of the material. So I want to identify a portfolio of products which I need to develop, build efficiency, and as you would expect, this single kind of step will not be enough. You need to probably iterate. So let's do that. Let's follow this kind of thing with a real case. My first real case 10 years ago, when we started lignocellulosic kind of feedstocks. So we are based on French technology. Organosol this particular part of organosol that saves lignin as a useful, valuable kind of part. And then the whole thing is how to develop portfolio products that holistically use, with best efficiency, the feedstock. So the different colors here indicate the different options you have for different products. You have to integrate in particular for each particular kind of product, as well as different production lines with each other. So the first part, as we said, is going to be flow sheeting, simulation, this kind of stuff that we usually do. And this is the kind of simulation that we have developed for the basic process. Yeah? I mean, this kind of simulation it would take for a conventional kind of flow sheet probably 2 days, 3 days. This took 2 years. Yeah? Why? Why? Because we didn't have thermodynamic models. The process engineering models, were not conventional ones. So we had to tweak around, models for many, many weeks and months before we converge into something, that is reliable. And this is the first message, that when you address this kind of problems, yeah, you are talking about a possible new generation of models, not models only for process, but models for thermodynamics. You cannot otherwise tackle this non-conventional type of substrates, non-conventional type of products, and definitely non-conventional type of process engineering kind of stages. And then again, AI can be in terms of hybridized models, as you want to keep the first principles, in place, and in a systematic way, embed and incorporate as much data as you have available, from the different experiments, but not now, wasting, all this information as you move from one kind of case to another, consolidating this information, for general use. Then the other end, the energy integration part came up, as you see here. I don't want to go through the details. I only want to show you what is the huge potential when you do biorefinery projects in terms of energy integration. Here you can take down the energy that you use, several, significant kind of percentages in savings, yeah? But as we have said, as we have said with other cases, the process integration is different as it is with conventional kind of streams. Why? Because process integration, conventional process integration, conventional energy integration, first of all knows what the hot and the cold streams are. Here in our case, we don't know, these are synthesis streams. So we don't know whether they are cold or they are hot. Yeah? We don't know whether they are large, or small. So CPs are variables. The essence of streams are variables. Yeah? So you have a much more complicated picture. In this complicated picture, you need to integrate mathematical optimization tools that will give you the opportunity to come up with a much wider space that you have, as well as conventional thermodynamics that you used before. It's an excellent basis to do the work. So here I show kind of tools that we have used for individual units, how to connect these units against a moving background of options. In this other case, how to retrofit an existing plant in terms of its solvents recovery part or its ethanol production part. Again, remember, this can be done automatically with tools. And this is a third case where this 39 megawatts of a refinery, through again combined use of thermodynamics and mathematical optimization, has indicated what kind of pressure changes are needed, but also what kind of restructuring, and integrated columns, are suitable to be able to actually have an energy-free type of separation for this kind of unit. You see here, the percentages, as in the previous case, have been impressive. So once you have all this kind of stuff, we said that the important, the exciting part, to come up with the portfolios. Yeah? So in this case, we have used Petri nets in order to translate the value chains, the conventional value chains, into things that we can formulate as superstructure. The value chains are not modular enough because they have overlaps, between the different parts of Petri nets, which is kind of graph kind of development. Can help you come up with superstructure that will tell about the selection of feedstocks and paths, or the selection of co-products, giving you suggestions of what you do, and going back to this French biorefinery, giving out what kind of promising products we have for each individual kind of fraction. Yeah. So you have now this economically, attractive option that you need to match also with sustainable options or LCA attractive options. So it's like a traffic light system. Yeah. You need two green lights, to go through, or a green and an orange. In our case, we were able to do that more or less, if you wish, through this kind of annotation case, and come up with a limited number of products to consider. So what we have now is we haven't had an exact portfolio. We have most promising products. Yeah. So we have tailored. We have pruned the large tree into a much smaller tree, and now what is left to evaluate is energy integration across different paths. Yeah. So remember, so far we have assessed, we have evaluated each individual kind of production line. Now what we are going to do is to assess how that is the scope to integrate one full path with another full path. If you really see, this is also covered in conventional kind of energy integration. This is what they call the total site analysis. But again, as it has been with conventional process integration, this is all on the basis of fixed streams. In our case, this kind of streams may be a different identity, may be a different capacity, may be a different thing. So again, you have to rely on kind of mathematical optimization plus thermodynamics part, where this is one part for the pretreatment, and then you have more or less a hyper cascade kind of formulation, which you can set up on the basis of thermodynamic values and optimize as a mathematical optimization problem. I mean, I can pass this one. Basically has mass balances around the graphs that I was showing before, as well as this hyper cascade, which is more or less a combination extension of the thermodynamic models that are used for targeting energy. So this kind of thing can be applied systematically to come up out of this kind of prune tree from the previous state, to come up with options that offer the better integration, and integration as account in terms of savings. Yeah. So these three kind of options here. So polyurethane, itaconic acid, and xylitol has been the best triad that secured the better integration. And of course, you all know that we can, using MLPs, have more or less integer cuts and come up with a full list of things as they can be developed. So here you can repeat this kind of stuff, and you can have a best top 10 type of list of products that appear to be most promising out of the 150 products which where we started from at the beginning. And well, because you have a systems approach, you can easily extend it. And then I can go quickly and see the number of extensions I have done. One of these has been in terms of multiple kind of feedstocks. So here you have 6 different varieties of feedstock. Again, 21 processes. This has been, again, a real problem in Hungary. This is Central Europe. And then you've seen, the kind of schedules that you can identify using more or less extension of mathematical optimization tools. Also, you can account for changeovers with respect to the different feedstocks that you have available. You can mitigate the extent of integration, and have safer or less intense kind of options, as we saw in these pictures. And as general, kind of rule that we more or less expected is that the larger the biorefinery that you have, the larger the scope of the integration that you have. Again, I'll go quickly through that. Again, you can address waste minimization, waste management around this biorefinery as well. Here you have a large number, 49 waste streams that you need to take care. So you can do that again, extending the superstructure, optimizing the whole thing, accounting for cases where you have a target, no restrictions, or setting up targets, or in this particular case, this was the real part of that, accounting for retrofitting, in other words, what kind of investment you would make in order to manage properly your stuff. And then in the end, you see that rather than you pay for that, you can identify some profit. So the cost lines that I was showing before have now become not a big, but anyhow is now a profit. We said we have a systems approach. Systems approach means we have a generic approach, so you should be able to repeat this kind of stuff for any other biorefinery. So I go to another biorefinery, very different now, the algal biorefinery. This is processing Dunajela Savina, yeah? This is a more promising type of product, yeah? And again, we bring up the same type of three-layer kind of system. The value chain is more or less this one. It's a new type of value chain now. And we have to do the same thing that we did before. And this is what we do. And basically, we have 4 different stages here: cultivation, harvesting, fraction extraction, and product recovery. So, and this is, the kind of stuff that where we need to identify the appropriate separation stages, the sequence, the integration between them. Yeah? But just to make a break and say, okay, what's the big deal? How about doing that in the more spontaneous way? Yeah, I mean, I go and identify one good product, I develop the biorefinery, and then go to the second product. I mean, the sequential, what we say approach. What do you miss out of that? Yeah, and actually, this is a historical kind of example, because this is how the Israelis developed the biorefineries when they did develop. So let's say, okay, glycerol is a nice potential for fuel. So this is the kind of flows that you can have. These are different compartments. Again, I go quickly. Single product glycerol. This is a biorefinery with a single product. This is unsustainable. Yeah, doesn't make money. Yeah. So right. So you go and say, how about introducing carotene now? Yeah. And as you introduce carotene, you see that you move from this flow sheet to this other flow sheet where things have changed. The sequence has changed. The process have changed. The integration have changed. Yeah? Well, if you do that, I mean, the good thing is that you have turned your losses into profits. Yeah? So from this viewpoint, you have done a good job. Yeah? But if you assume that you have done the sequences before, yeah, you are actually, changing the whole plan into a completely new kind of thing. And if you do that continuously with other products, so here we had the glycerol, we involve carotenes, then carotenes, if they involve xanthophyllus, or if they involve galactolipids, yeah, then you go from 1 to 2 to 3 to 4, and then you see that the flow sheet continues to change and completely, yeah. So you can say that the simultaneous approach is a good way to burn money, yeah, like water, yeah, spend money like water. So the simultaneous approach works differently. The simultaneous approach brings everything, as we said, together. And if it does this one, it identifies the different options, processes, products, yeah? And then you can build these you can build these superstructures, as different instances there. And you can optimize superstructure for a number of cuts. And what you get at some sort of target profile, you may say, yeah? Where for each different region, you identify select number of products, select number of processes, select number of portfolios, yeah? And this number of, or the actual type of processes and products and portfolios will come up, through this kind of graphs that identify more or less what are the most critical kind of process for you to involve if you really want, to optimize these different options. And this is in terms of products, you see what kind of products appear to me more profitable. Algal biorefineries produce specialties. And specialties, we never want to have large kind of volumes, yeah? Because we shoot our own feed, yeah? We need small kind of batches, yeah? And there is a challenge there. What am I gonna do with my plant for the remaining of the year? I do produce in a batch for a month, for 2 months, yeah? And then how about the other months, yeah? So multi-algal biorefineries and flexibility in terms of, cases where some of your products, may be, cancelled by FDA or, whatever, what are you gonna be doing? So, because again you have a systems approach, you can use this one to formulate multiple kind of strains, as I will show here. So here you can have different kind of value chains from different kind of strains and develop these designs uniquely for all of them. Yeah? So this is design a biorefinery that will not treat only one algal strain, but multiple algal strains. So I will illustrate that with a real case where we have Dunayella, Haematococcus, and Chloropsis. Now we have three kind of strains. Yeah? So we repeat what we were doing before. So these are the three value chains, like the ones I was showing before. Yeah? You can concatenate these graphs, and these are different products which are common, and you can develop, for each one of them, of course, some sort of design. You can design, if you wish, a biorefinery like it doesn't exist. The other ones that do not exist are options. This is the second one with Haematococcus. This is the third one with an Chloropsis. But now we go into this kind of unifying thing. Yeah? So we take, as we said, the different type of value chains, yeah? And we create a single value chain. Yeah? And this value chain is the one we optimize. And as we do that, we have min-max type of constraints. We take the minimum of the maximum piece of equipment that is good enough to process, each particular batch. And then you see more or less the difference. The flexible biorefinery apparently will cost you a little bit more, but this is more than each one of the other ones. But this a little bit more will let you operate, for all the different kind of strains that you may have. Yeah. So some additional investment, you make your biorefinery much more flexible as it was before. Before again, it was just one strain. Now it is going to be for as many strains as you're going to put in the system. Now, just to take some water.
It's an important resource.
It is.
Renewable.
Yeah. All right. So there is a particular challenge when you do biorefineries, yeah, or when you develop, this kind of new industries, to integrate, with urban and municipal streams, yeah. So there is this additional kind of consideration you need to make, and in this consideration, the sustainability is not in terms of indicators, LCA type of indicators, yeah, but it is in terms of closed kind of fluxes, streams, yeah. Because sustainability, industrial ecology type of paradigm, has to mimic a living, kind of system that has closed streams and, closed streams around their operation. So this is, also the basis of the circular economy kind of concept, yeah. So sustainability has to be along these steps. Now, where you have industrial flows, you have urban flows, yeah? So, and ports have been a natural bridge between these two, because industrial ports are not exactly industries, yeah? They are not exactly in urban territories. So it's a nice kind of territory to bridge industrial and municipal flows, as addressing this new challenge. We have done that in industrial ports in Europe, and I will show more or less examples of what I have presented before. Now, with respect to the ports, now we have to integrate again. Now we integrate industrial and municipal kind of fluxes. Malmö is a port in Sweden where we started the work, and this has been collaboration with E.ON, yeah. And here is the kind of network that you develop, and this is the kind of energy that you can exploit out of the interactions, again, between these two flows. Wismar is a port in Germany, which is former Eastern Germany. As you can tell, Germans are detailed to record every bit of part, which is there. So this kind of graph appears to be very detailed, but the potential has not been as great in the end. It's 16 megawatts. This is Greece. This is a port actually which is under sale to the Arabs nowadays, and they have used this kind of study, to convince about the potential. of Astrakos. This is 20 megawatts, it's slightly larger than the German port. And the most successful one has been a port, which is not exactly a port, is Mandova. Mandova is a river port that connects, through the river to Venice, whatever. This is former kind of site close to a conventional type of industry. And this is the kind of network that they have developed, but they have a very impressive kind of energy that 681, this is the number, 681 megawatts, yeah, close to 1 gigawatt. And this is now the basis for a biorefinery that has started construction already. So if you go back to my slide, this Mandova is one of the sites. When we address industrial and urban flows, we typically engage geospatial, spatial kind of platforms. Yeah, we have to challenge these product passports, and we are using also some game theory. I will very quickly touch on these ones. This is more or less a geospatial platform that has been integrated with such an urban network, and with a view to become an observatory, for actions in different parts of my country. This product passport, I don't know how much big is this one. Yeah, it comes with the obvious, challenge that waste is not used extensively and sometimes at all, because industry doesn't know what exactly it buys. Yeah, so there is this effort to combine measurements, which are numerical measurements, but also images, from spectral, whatever, you have available, yeah, what you call process analytics technology, advanced process analytics technology, into some sort of IDs that could make, trade up the different waste streams from one side to the other. I will get back to this issue later on when I talk about AI, because AI has a big role, into developing this one. Game theory, why we need game theory? Well, game theory is applied because this kind of industrial, urban kind of interactions involve different stakeholders. So we need to understand policies and roles so that we have win-win type of safe or stable win-win solutions. And these win-win solutions are different from the win-lose solutions that were familiar from Pareto kind of analysis. Pareto, yeah, is win-lose. You win something, you lose something else. Whereas there are win-win solutions where actually have what you in mathematics identify as non-zero-sum type of games. Yeah. So the pie becomes larger, because you're talking about a new space. So this win-win solution has material to keep everybody, happy. So we have done this one in a number of cases, not that many, but a number of cases. One is in municipal solid waste management, where we identified that there was no nice equilibrium in what we have today. In marine lubricant markets, to understand threats in emerging kind of businesses, and to also understand the potential of circular economy to stabilize this picture on the left. I don't have time, or this is a separate lecture and so on. Yeah, but I can share some of the stuff. As far as municipal solid waste management is concerned, again, the important part is that what we have today doesn't account to a nice equilibrium type of point. That's why people are bypassing legislation and they do things differently. Yeah. The other part is that Stuck-Kilberg problems, which are being a baseline or a reference, for analyzing duopolies and this doesn't hold exactly in the case of circular economy. The reason is because for in circular economy paradigms, or actually in municipal solid waste paradigm, the money that you get is from the raw material. It's not from the product. Yeah. So once you get the raw material and the money, you have no incentive to go into anything. You just dump the waste in the night, and you make better profits in this way. Circular economy, from what appears, is a way to stabilize that, but not necessarily stabilize that. Depends on what of technology you bring in, what kind of products you bring in, an important now conclusion that has come up out of that is that the first player doesn't necessarily get the better benefits. The second or the third or the fourth has also good promise to do things. So, okay, I mean, am I doing all right with time?
Oh, you sure.
It's okay?
The moment.
All right, let me, okay, I mean, I can go as quickly as required, but I'm switching now gears, from the better quality type of biomass and organic type of substrates, yeah, into waste-based, because waste-based, is apparently not just less expensive, it is actually income, yeah. So this is, but it's also quite abundant. So I gave, this slide, from plastics. Plastics is a big, innovation line, inspiration line, I want to say, about things that we can do. You burn all this, or you use all these millions of tons per year, yeah, more or less to dump to let to the sea, or dump, in landfills, or incinerate, and only 2% actually is recycled. If you go to statistics, they will say 60% is recycled from the plastics. This is wrong, yeah? 60% is collected, yeah? And when they say they collect it, then they do all these other things. They don't do, of course, this one, but they do this other one, yeah? So nothing is actually recycled with a huge amount of fossil fuel. So, I mean, the future, the picture of the future, I'm sorry, is to have some part of that, as renewable feedstocks, say biomass or whatever, but some other one to be able to recycle chemically, apparently, yeah? Either, finding ways to register this properly, or find ways to change the way that you produce plastics. So, this is the plastics. These are some figures about the kind of volumes involved. You see that food waste, I think you do work in food waste, is the most abundant type of waste that we have. Then second to that is municipal solid waste, which to some extent is food waste. And then you have, you have construction material, which is outside our chemical engineering areas, and then textiles, yeah? So the next project I am presenting is about textiles. Textiles has a value chain, remember the value chain where we start from, which is huge, large, yeah? I remind you that the 4 kinds of components of textiles are cotton, yeah? Cotton proteins from wool is polyesters and polyamides. These are the 4 major chemicals. And out of these, you can create lots of other stuff which are shown here, with the different colors. We couldn't afford to, to have partners for all this kind of entities. So we had, a smaller version for textile, yeah, where again the different parts became different things. Terephthalic acid became bottles, ethylene glycol became produced fibers. Polyamides, because Arkema wanted to produce threads again from this one, became acrylic acid. And the cellulosic part, ethanol and proteins, from the wool became biopolymers. Yeah. So with this kind of stuff, we had also partners that this was about 450,000 tons per year collected by the Germans using French technology. Yeah. But we had also people who had good sensors, to separate the different fibers, and our role was more or less the modeling and the design part. And it hasn't been in any other biorefinery the systems part to be so useful than in this particular case. Because it has, this kind of cycle more or less took about 4 or 5 years, to converge. And you have to resequence the technology, you have to change the technologies, you have to think about industrial symbiosis type of opportunities before you convert to something useful, and systems engineering has been instrumental in order to give you guidance in how to do that. And even so, in the end, this thing wouldn't be profitable unless in the context of circular economy. In what sense? You had to use not virgin type of chemicals, not virgin type of solvent, but try to get this kind of chemicals from nearby industries where these things were not pure enough, but were waste, yeah? And the small streams, the smaller streams, would be possible to get rid of, sell, pass, to other industries where we're doing, a much larger scale type of activities. For instance, cellulosic streams were not considered in this refinery because they were very small streams. They buy the smaller streams, you better sell or give even away for free to other kind of industries that were producing ethanol in a larger scale, so it was more economic to act in this way. I've talked about bioprocesses, so I bypassed, the other important part, which is CO2 as a feedstock, or hydrogen and thermochemical and biochemical type of things. CO2 on its own has a separate kind of value chain. Some of the paths are with high TRLs, like production of BDX, Some other ones, have lower type of readiness levels. A similar case is hydrogen, Hydrogen, hydrogen economy, everything is about hydrogen, but we don't really know what hydrogen should be used for, Definitely shouldn't be used for energy fuel, but should rather be used as a feedstock to other things. Hydrogen can be produced either from biochemical routes, dark fermentation, but apparently, it's more abundant, from other type of renewables with which, there is a line to integrate, solar, whatever else, they have hydrogen as storage. You can produce even hydrogen from chemical paths, like gasification, chemical looping, without looping, gasification, and it can be used, to promote the production of other different type of products. And of course you can combine these two value chains, as I have here in the case of a refinery, where the hydrothermal liquefaction of a thermochemical path can take waste kind of heat from a refinery, use the hydrogen from a refinery, use the water from a refinery and contribute the biocrude to a refinery, whereas say an algal biorefinery can capture the CO2, make use of the water, So, these kind of interactions are also possible. But, at least in Europe, the e-fuels, I don't know whether you use this kind of terminology here, electrified kind of fuels. E-fuels is a big trend. The ThyssenKrupp project in Germany is one case where actually you combine CO2 type of capture with hydrogen to come up with methanol, and then from methanol you can produce other things. Of course, methanol is not necessarily a path to integrate CO2 supply chains and hydrogen supply chains, but is one typical project. An illustration of e-fuels to connect with my presentations recently this week in Orlando, related to marine fuels. And marine fuels, they are looking for these e-fuels to come up and replace their conventional fuels. At least in Europe, they are not interested in ammonia. So alternative fuels can be LNG, which is a fossil fuel, or methanol, which is an e-fuel. Ammonia, as I said, they're not interested in. Hydrogen and biocrude, they are the options. And I will show the results of integration. So the whole idea, other than the alternative fuel, is also to capture the CO2 on board. So as the ship, travels, to be able to capture the CO2, store it at the ship, and then drop it, at the port, in some way. So here is the huge potential in terms of sustainable LCA analysis. And here are the, of course it's too much in these slides, these are the integration potential for each one of the different fuels. Just the integration itself is not any significant number, 2 to 4%, a savings of fuels, But the important part is this. You can integrate, CO2 capture 80%, 80 to 83%, close to 80%, or even 40 to 47%, without putting that much additional energy. The integration can more or less help you with a little bit more energy, to be able to capture what you do. And in the case of LNG, which again is a fossil fuel, you have, because you have, a subabyant cold stream, you have cryogenic separation more attractive than the amines. Yeah. So why is that? Again, because LNG is stored in very low temperature, so you can use this cold stream from the subambient to the ambient temperature to capture some part of the CO2 emission, of the CO2 in the emissions, yeah, and liquefy that. It also opens up new ways. Again, the systems approach opens up new ways to re-engineer the Wärtsilä engines that are used in the ships. Why? Because Wärtsilä engines today, they use an excess air, more or less because they want to get rid of methane. Methane is a big issue there, yeah? And they use a ratio of air to fuel almost 60, yeah? Whereas thermodynamic kind of ratio is about 15, yeah? By doing this liquefaction, of CO2, then you can let the efficiency of the CO2 be less, yeah? Since you're gonna pick up anyhow the methane and the CO2 as liquid, then you can recycle it back to the engine, yeah? So this is an idea for this kind of stuff, and you're talking about multi-million, apparently, kind of business, yeah? Its SIP is $500 billion. Another case where, which I saw here is a pilot actually that we have set up in Greece, which is hydrothermal liquefaction. Biomass, we said, is plentiful, but biomass has a lot of water, yeah? So thermochemical processes, like gasification and all that, are not as efficient, again, because of the water content, with the exception of hydrothermal liquefaction that uses water in order to break the biomass, into smaller parts, yeah? And again, in that sense, you can use biomass from everywhere, from sewage, from algae, from wherever they come from, yeah? And this is an idea of the pilot. This kind of technology has also this interesting potential. It can integrate itself into a very compact way, so you can have a standalone kind of unit, yeah, that can operate on its own, or you can integrate that with a refinery where you can upgrade and hydrogenate the product into much better kind of case, yeah? So you can work on small scale, you can work on large scale. The trade-offs are different as you go into the different scales. So if you have a refinery nearby, apparently you have a trend, or an incentive to share with the refinery. If it is in an isolated area, in India or wherever, so there is no refinery over there, then this kind of part can work as well. Yeah? And this is more or less pictures of the same stuff. I'm closing my presentation, so your patient, will only need to last for a few more minutes. Yeah. I close this presentation because with a statement on this, that very little of what we do now for renewables would be possible without data engineering technologies. Data engineering and technologies are instrumental for us to cope with these new problems. Yeah? I will show some slides more or less to whet your appetite, and we'll stop there. These are tools we have worked in the past using more or less metadata and workflows to automate all these kind of schemes that I was showing before. Yeah? So this kind of stuff can use logic in order to consolidate information from a metadata into kind of superstructures automatically, and this is thing that we have in our libraries, and come up with automated solutions and apply in high throughput kind of work. Another piece of work that we have done in the past is what we call as ex-ante LCA, where actually we have transformed the conventional way where we calculate LCA kind of metrics, which is something that starts with background type of data, where we create some flow sheets that you call basically foreground data, and then you calculate things, and this may take 6 months, 8 months, whatever. And then, you do that again, and as you do that, you don't know what you're gonna get at. Whereas, since we have done a number of cases anyhow, so this kind of stuff has been done, for so many other cases, so looking at that as a data flow problem, it's a background, foreground to LCA, and this foreground, can be replaced either by a decision tree or an artificial neural network, yeah, that will be trained both from the flow sheets and the foreground data that you have generated over there. And this has worked reasonably well to select in advance products, that appear to be sustainable, or select in advance technologies that are promising. Yeah, that hasn't worked very well when you go outside this kind of training set. Yeah, but it's another one. Now, I'm closing with things that we are doing, is work in progress. Yeah, one is to characterize products, as I said, and feedstocks. Yeah, this is a big challenge there. How are you going to characterize using, the knowledge that we have today, things that, for instance, you produce from HCl that looks like this one. Yeah, this is, like a nasty liquid, thing, that you don't know what it is, and no refinery will ever pay for anything, for this product unless they know much more about that. So the kind of stuff that you need to integrate are temperature boiling curves, as they are shown here, or kind of, spectra, that you have, produced, separately in the labs. And this we would like to have as kind of stamps, that we can use. The other one is these are twins for complex processes. Complex processes like the HDL, or like what I will show in a while, bioreactors, yeah, where you can set up models based on first principles, yeah, but these models are inaccurate. So you need to integrate and make use of data, as we said, earlier on. Another area of application is where you want to vertically integrate models of different scales, and then you can use equation-free type of interactions between, or integration between models from one level, one level of details, to another level of granularity, you may say. One level of granularity to another level of granularity, yeah? The domains are set up on different principles, first principles, yeah? So the integration between the kind of stages is not possible. However, using data streams instead of assigning and matching equations from variables from one domain to variables of another domain, data again streams can bypass that. Plug and play integration, is very useful when you have a reactive separation kind of systems, and these are very common in bioprocesses for the basic reason that water is abundant and the organics set up as a tropic type of pictures that is difficult to separate. So in this case, you need to involve some sort of entrainers. Entrainers can be used in different ways, or different type of process can be integrated with the reactor, like membranes, like absorption, yeah? So this integration of different modules with each other can be done along these lines. The last part relates to an even more ambitious effort as we try to combine systems biology with process systems, yeah, or systems engineering. So systems engineering and systems biology can be integrated with what purpose? The purpose to build strains which are custom-made to perform against particular substrates or towards products. Industrial biotechnology is a beautiful domain where you can build chemistries theoretically as you wish, yeah? But these kind of chemistries are not necessarily fast enough, or are producing a number of other byproducts that or inhibitors that you cannot cope with. So building these interactions between these two is instrumental, and this is the work that we have done in collaboration with EPFL, not the EPFL that you know, but another group in PFL, where again we actually try to integrate two different domains. In one domain, in process engineering, we have a good set of first principles for the bioreactor. Yes, we don't know everything, but it's at a good level. And in systems biology, we have the strain, the microbial organism, for which we know very, very little. Actually, the balances that we can write for this system are not accounting for a simulation model, account for what you may call convex kind of analysis. Yeah? So you have a polyhedron for which you know that your operating system belongs into that. Or if you see that mathematically, you have more variables than equations. You can arbitrarily fix, kinetics to come up with results. So what we do there is we curate kinetics. We curate kinetics arbitrarily, with permutations, in a systematic way, but arbitrarily, yeah? We create millions of populations of kinetics. Then you do clustering, classification, so you identify a discrete finite number of clusters, and then you try to match the real-life kinetics with the clusters to configure what could be the most representative kind of option. And by doing that, you don't only discover the kinetics, but actually you have a way to convincingly go back to the strain, modify the strain, yeah, in a way that can deliver what you want to deliver. So this is a big promise, of course, yeah, but it's a starting point there. And then this, what I said before, you can go back to the genes, you can go back to the from the metabolomics to the proteomics, transcriptions, and genomics, back and forth, upstream kind of stages, and create things as ways. I conclude here. I don't even want to read the remarks, yeah, because you are already, exhausted from this. Apologize for the late start, but it's the responsibility also. So rather than that, these are things, these are collaborators. I would like to stop here, and take questions if there are any, and thank you very much for your presence.
Thank you very much for a very impressive presentation and amazing things. So I know we are running a bit out of time, so if there's any quick question. Actually, I have one, maybe just to kick off. So you mentioned about marine fuel, right? This e-fuel concept is very interesting. But what do you think will be the major energy source for marine transportation in the future? Because it seems like every single listed doesn't make sense. None of them is optimal. So what's the optimal choice then?
If it is, I mentioned methanol. Methanol can produce from CO2. And CO2, you have an obvious resource.
What about the cost?
Sorry?
What about the cost?
The cost to convert?
Yeah, the whole system.
The cost, I think methanol is not that much the cost only. It is the fact that you start from a fuel, you have CO2, which is from the combustion of a fuel, yeah? And then if you end up into fuel, from an LCA perspective, you are actually fooling yourself. However, in the way that I presented on board, capture on board, yeah, you don't release the CO2 from the combustion because you capture and you take it back to the system.
But then how would you handle the CO2? Even if you liquefy the CO2, how would you do it? Just using it in the
You liquefy. You liquefy. Because the methane is liquefied at minus 160 degrees. Yeah? And CO2, is minus 80.
But eventually it will go up, right?
No, because you capture it. The whole idea is you burn, the fuel, whatever fuel you have. Let's say you have LNG. LNG is a fossil fuel, yeah? You burn, you emit CO2, but you don't let it out. You liquefy the whole stream. You store it in the same type of tanks that you use for LNG, the same type of tanks, not with LNG, but the same type of tanks, yeah? So you store it there, and when the board, reaches the port, then you drop the CO2 there.
Then what to do with those liquefied CO2?
The CO2, if you have a production for methanol, it's feedstock.
Alright, that's interesting.
This is LNG, but this is what I said, it's methanol, where you use, CO2 as a feedstock. If you talk about biocrude, biocrude is, I didn't have the full presentation apparently, but biocrude appeared to be the best choice. Biocrude, remember the hydrothermal liquefaction? Biocrude can be produced from hydrothermal liquefaction. The problem with biocrude is that unless it is pure, yeah, unless it doesn't have this kind of, it's not homogeneous enough, yeah, then as you burn it, you create other things like sulfur oxides and stuff of that sort, for which, things are, you need to take care of these ones as well.
Thank you.
Yeah.
There
is a challenge for CO2 capture, I have to mention, which relates to the cost that you mentioned. When you capture CO2 on board, it's much more expensive than if you capture CO2. The reason is, wake up, the reason is?
Smaller scale?
Sorry?
Smaller scale of capturing?
No, the reason is that it is much more diluted. CO2. When you have a heavy industry, cement industry, the CO2 comes with a large kind of concentration. To capture is less expensive. Yeah. To reduce it by X%. In the industry, it is very dilute. So you have to have an expensive kind of amine system to manage this one. Yeah. So that's the reason. The other thing, as I said, however, is companies like Wärtsilä, which is dominates at least in Europe. I don't know what is the dominant kind of manufacturer in US. I don't know. I mean, ExxonMobil is developing engines as well.
Oh, engine, GE maybe.
Engine. Wärtsilä is engine. Yeah. Wärtsilä are more or less they are producing 80% of the engines that they used for ships. Unless, I mean, they are more or less mechanical engineers. Yeah. So that is the advantage of being a little bit of a chemical engineer. Okay. Because what you actually do is, you want, as I said before, you want to minimize methane slip. And if you really see, besides all the regulation that has been introduced in the marine industry, the environmental burden has increased. Why? It has increased. Why? Because they release methane rather than CO2, and methane is 4 times more, impactful than CO2. So overall, the big picture, is not improving. Yeah. So in order to reduce methane, they run. Let's say it's like a reaction. They run this reaction with excess air. So as I said, it is 15 thermodynamically. This is the most efficient ratio. 15 air, 1 fuel, and they run it to 60. Why they do that? Obviously, they won't dilute the effluent because you have more air, so it appears good. Second one is like in a reactor. You put excess of one feedstock to have a very high conversion of the other. However, what we said, CO2 capture is like a separation thing. If you capture the methane, if you capture the feedstock and you recycle it back to the system, then it's completely different picture. But if you are a mechanical engineer, you don't understand that because you just burn fuel. This is what you have learned to do in your life. Yeah. No, full respect. I hope because we have mechanical engineers here.
Yeah. Some actually.
Some. So apologize.
Anyway, so maybe we conclude here, and then please feel free to stay around and talk to Professor Kokossis. Thank you so much again.